Good morning. We still have one more exercise from our sheet number 9.1 about vector functions, or more clearly speaking about radius vector functions, as I tend to say, not to mix it up, in order not to mix it up with vector fields. Vector fields actually will be our future concern or our next concern in sheet 9.2. So let's keep this apart. We're still talking about most of the cases about curves, often curved in space, you could say, in a three-dimensional vector space, but also sometimes, as in this case, we're talking about planar curves. And one of the very interesting special sorts of such curves is the so-called cycloid. It's called cycloid, as you can see. The naming refers to sort of circular geometry behind it. On the other hand, there's a special reason why this sort of curves gets its own phrasing, not to mix it up or to to confuse it with something like circle or even cosine, sine. All these curves have a certain relationship to circular geometry. Now, before I go into detail, I just show you a little sketch, and then because I think it's well, you feel more comfortable when starting the calculation if you make yourself familiar beforehand with what's it about, or how does this curve how is it constructed. Okay, and here you see quite easily what happens. You must regard this black circle also here and here as sort of an auxiliary object. Actually, it is. It's sort of a construction tool, and the curve of interest is the orange curve called the cycloid. At first sight, you might think it's sort of a circular bow, or even part of a sine or cosine curve, like the positive semi-wave, you know, as we call it. It's neither nor. Actually, it's really a very special and different sort of curve, which is called a cycloid. So, and look at this circle here. It's auxiliary. It has a radius of, let's say, constantly capital R. Okay, so that's why if it sits in the origin here, that it means that this the y coordinate at this position, of course, is 2 times this this radius capital R. So that's the diameter of this auxiliary circle, of course. So now imagine this black circle just rolls to the right. It rolls to the right along the x-axis. So, and if it now the next important issue is you have a certain highlighting, or let's say this dot here, this orange dot, it's like a mark which you put on the circumference of this circle at this position, but it's fixed. It means as soon as the circle starts to roll to the right, this mark here rolls upward. You see, it rolls upward, but at the same time, it, of course, it's connected with this circle, so it goes to the right and something like up and to the right. So this is what you would see if this is a lighting. Just imagine it's sort of a little lamp, and you would see this this lamp lighting along this curve here. So that's how the curve actually originates. It's quite interesting by itself. Let's just check it. Imagine this circle has performed a half rotation around its own center. It means that this mark, of course, is meanwhile in this position here. Also, since the circle rolls along, it sort of rolls about a distance which corresponds to its own circumference, but by arriving here, it has only rolled along half its circumference. So that's why the x-coordinate must be pi times r at this position. Is clear what I'm saying? Because after a full turn around itself, the circle arrives here, and it must have traversed a distance of 2 pi times r, because this is its full circumference. So that's quite clear. And also this up and down movement is clear, but the exact form of this curve, this is something for the algebraic part. It turns out that it's very well described by this radius vector function. You see that the auxiliary radius is also put in here, and it's a certain combination of sine and cosine as expected. It's important to know that with the x-coordinate, there must be a linear contribution of t, which is due to the movement of this auxiliary circle to the right, but also the vertical component has a constant of 1 here. But we can just check it, and one way to easily check it is putting, well, this is not really a proof, but just setting t equal to pi. We must remember that the auxiliary variable t is sometimes, it has something to do with the angle referring to the x-axis, but not always. In this case, it's sort of the rotation, you could say the inner rotation position of this auxiliary circle, whatever. But let's put t equal to pi, and then see that we have, where is it? Here, we have r times, here pi minus sine of pi. Sine of pi, of course, is 0. So what remains is p times r for the x component. Also, we have r times, parentheses, 1 minus cosine of pi. And since cosine of pi equals -1, we have a factor of 2 inside here. So 2 times r is the y-coordinate. We can shortly check this. This radius vector, you see it in blue here, has exactly pi times r to the right and 2 times r upward components. So that's correct. Also, we see that the curve, even for symmetry reasons, it's quite easy to see that this must be a maximum point of this curve. Okay, so it's quite clear that the tangent would have a slope of 0. This is the green dotted line here. But also we can easily calculate in red, you can see it here, our well-known tangential vector, the tangent vector, u vector dot of pi, where t still holds a value of pi. And this is what I'm doing here. So the first step, as always, is find the tangent vector by differentiating these components separately for variable t. I'm doing this by saying, okay, the factor of r is constant, it stays there. Then in parentheses, t gets differentiated to be 1, and sine gets differentiated to be cosine of t. The minus sign stays there. Also, this is an additive constant which disappears by differentiating, while the cosine of t has a derivative negative sine of t. So this minus changes to a positive sign in the end. So we get r times sine of t. That's quite easy. And now we can insert t equals pi, and we get r times 1 minus, again, cosine of pi equals -1, of course. So we get 2 times r this time for the x component, while the y component gets 0. Sine of pi, as you know, is right in the middle of the sine curve where it reaches 0 again. So that's it, 2r and 0, and that's what you see here, the red vector, which correctly describes the tangent direction, and also, as you know, its absolute value sort of describes the speed by which this curve is transversed momentarily. So that's quite a nice view. Now, it may seem strange to you, and I'm not even sure whether you found this specialty in the lecture script, so I just explain shortly. The question is, can you calculate the slope, which is denoted with y prime of t? So that's a little, let's say, unconventional. we are all used to the notation y prime, which usually refers to the x variable. You know what it is? It's just the slope referring to x. Just a second. No, that was my mistake. I'm sorry. I must. Oh, I can't even stop this. I'm sorry. This was a mistake. Just a moment. Stay calm. Here I am. I don't find. Yeah, here it is. Okay. Now let's proceed. So we found, okay, I was trying to explain what the notation means, y prime of t. Well, it's important to remember that in this case, especially, our auxiliary variable t is not the same as x. We can see it here again.
We can't see your screen still.
Oh, I'm sorry. I must have stopped the screen sharing by mistake. Thank you for the hint. But I hope the recording is running. I think so. Thanks for the hint. Okay. Okay. Now, is it fine?
Yes, it's fine.
Okay. So you can see, for example, this is our x position for t equals pi, and there's a factor of r additionally here, also here. So you could easily say, or just suppose, and it's correct, x is generally the value of variable t multiplied with this radius capital R. So that's the difference between x and t. Anyway, now you see the problem is, as soon as I set t equal to pi, this expression looks like sort of the slope at x equals pi, but it's the slope at t equals pi. So I must criticize myself because my notation here is not quite clear. You should make it clearer by just denoting y prime of t equals pi. That would be the best idea, probably. Perhaps I should do it also. And still, it's quite unusual to do it this way, but it's to be found often, also in the literature. I should denote t equals pi, so then it's clear. So don't be confused about this notational issue. It's just an interesting question. Can we calculate the classical slope by using our vectorial derivative? And that's what it's about. Okay, it's quite simple. The formula that you find tells you that the slope at any value of t must be the relative ratio of change of rate of change of the vertical component in relation to the rate of change of the horizontal component of the u vector. That's all. Okay, so it's like constructing sort of a, let's say, well, you can't see it easily here, but let's just imagine we would have a certain tangent, for example, here, and then we would say, okay, we need sort of a slope triangle, and we can express the sides of this slope triangle. We can express them by the rate of change of the vertical and horizontal component of the radius vector. So sort of this. Okay, I don't have the time, of course, to derive everything here. I just wanted to make it a little more vivid for you to understand. So anyway, we just take the ratio of these two, and we just found them. It's the, is it? Oh yeah, the second comes first. So r times sine of t is in the numerator, the other expression in the denominator. And then it even simplifies because the radius cancels out here. And that's nice to know because it means that this is a situation which is not dependent on, or let's say it's independent from the question how the scaling of this cycloid curve is. You know that the r parameter is nothing else than a scaling factor, a linear scaling factor. So anyway, setting t equals pi, we get y prime at t equals pi equals sine of pi here, and over 1 minus cosine of pi. Again, this is 0, this is -1, so we have 0 by non-zero, which is always and clearly equal to 0. And that's just, well, the confirmation that the tangent is horizontal at this maximum point. So that's actually all this little additional exercise was about.